For decades, we've all heard the promise, right? Nuclear fusion is supposed to be the clean, limitless energy of the future. But what if that incredible dream is built on the same shaky ground as another failed nuclear technology, one that most people have already forgotten?
So let's just get right to it. This is the question at the heart of our entire explainer today. It's a pretty bold comparison, putting the bright future of fusion right next to the failed history of the fast breeder reactor. To figure out if it's a fair comparison, we really have to dig into what went so wrong.
Here's how we're going to break it all down. First, we'll look at these two dream technologies side by side. Then, we're going to explore three massive walls they both slammed into: a technical wall, an economic wall, and a really nasty one called the curse of neutrons. And all that will lead us to our final, maybe surprising, conclusion. Okay, so to really get why these two very different technologies might be doomed to fail in the exact same way, we first have to understand why they were both seen as the ultimate prize. Two separate paths to solving humanity's energy problems forever. So you've got two different approaches here. On one side, the fusion reactor, which aims to create energy by smashing light elements together. On the other, the fast breeder reactor, designed to actually create more fuel than it burns by recycling heavy elements. Now, their methods were totally different, but their goal? It was the exact same utopian vision, to create a nuclear energy system that could power the world for thousands of years with no fuel shortages.
But dreams are one thing, and physics is a whole other beast. Both of these grand visions ran headfirst into a brutal technical wall. It all boiled down to a fundamental problem of control.
100 million degrees Celsius. Just let that number sink in. That's the insane temperature you need to get fusion going. And since no material on Earth can handle that, scientists have to use these incredibly powerful magnetic fields to bottle up the super hot plasma. But here's the catch. The plasma just refuses to cooperate. It's fundamentally deeply unstable. It leaks, it collapses, it flickers in and out of existence. There's no sweet spot where you can just get the reaction humming along smoothly. It's not like a steady campfire. It's more like trying to hold a bolt of lightning in a magnetic cage. And this is where the parallel gets really interesting. The fast breeder reactors had a very similar problem. Their reactions were so fast that they were constantly teetering on the edge of a runaway chain reaction. For both technologies, that window of stable, safe operation was just terrifyingly narrow. And even if you could control them, the very materials you build them with couldn't survive the intense heat and radiation for very long. Okay, so they're incredibly hard to control. But maybe we can just engineer our way out of it by building them bigger and better, right? Well, that leads us straight to the second wall they both hit, the economic wall. The thinking was pretty simple. In theory, if you make a reactor bigger, its volume and therefore its power output grows way faster than its surface area. So the cost for each watt of electricity should plummet. Bigger should mean cheaper. But it was totally wrong. In the real world, the cost of all the complex machinery, the magnets, the cooling systems, the shielding, it grew so fast that it completely wiped out any economic benefit of going bigger. The savings just, poof, vanished. And this chart just lays out the brutal results. At the gigantic scale required for fusion to even work, it offers zero cost advantage over a standard nuclear reactor we already have. And the fast breeder? Oh, it was way, way more expensive. They basically scaled themselves into being completely unaffordable. And look, this isn't just a theory on a spreadsheet. We have real-world examples. Japan's Manju project cost over 1 trillion yen and barely ran at all. France's Super Phoenix was a similar disaster. These things were technological marvels that, yes, could technically work, but they were economic black holes. They were completely and totally meaningless in a real-world energy market. All right, now we get to the third and maybe the biggest deal breaker of all. This is the one that really challenges that whole clean energy myth. We need to talk about the curse of the neutron. 14 mega electron volts. Now, that number probably doesn't mean much to you, but for a single tiny subatomic particle, that is a colossal, staggering amount of energy. When a neutron gets shot out of a fusion reaction with that much force, what do you think it does? Well, it creates an environment inside the reactor that is 5 times more radioactive and damaging than a standard nuclear fission reactor. These high-energy neutrons are like a constant, microscopic sandblaster, just tearing apart the very structure of the machine from the inside out. So what does that actually do? Well, first, the reactor walls get incredibly brittle and have to be replaced all the time.
And guess what? Those discarded walls are now highly radioactive waste. So while the fuel might be clean, the machine itself becomes a huge source of radioactive junk. And the worst part? Neutrons don't have an electric charge, so you can't steer them with magnets. They go wherever they want, smashing into everything and causing unstoppable damage.
So let's pull all this together. We've got a technical wall, we've got an economic wall, and we have this inescapable radioactive curse of neutrons. When you stack all that up, what are we left with? We're left with what you could call the scalability trap. It's a classic catch-22. Small fusion reactors are physically impossible. The plasma just won't stay hot enough to keep the reaction going. But large reactors, the only ones that could work, are economically impossible. They become so mind-bogglingly expensive to build and maintain that no one could ever afford them. They're trapped between what physics will allow and what economics will tolerate.
And that leads us to the final and pretty brutal verdict. Fusion is theoretically possible, but socially impossible. Yeah, maybe you can build one, but you can never actually use it in a practical, meaningful way to power our society. So that brings us right back to where we started. To say that fusion is as impossible as the fast breeder reactor, it isn't just trying to be provocative. It might be the most accurate way to convey just how serious and how fundamental the challenges really are.